Ionization energy is the amount of energy required to remove an electron from a gaseous atom or ion in its ground state. For example, the first ionization energy is removing an electron from an atom, whereas the second ionization energy requires removing an electron from an ion. The first ionization energy is always going to be the lowest of the ionization energies, and each subsequent ionization energy will be larger than the previous one. From the table, you can see the small ionization energies for metals and the large ionization energies for nonmetals. Also, look at lithium. The first ionization energy is about 520 kilojoules per mole, whereas the second jumps to 7,300 kilojoules per mole. What's going on? Graphing the first ionization energy versus the atomic number, we see that the largest jumps in energy come when we remove electrons from a filled shell, such as in helium, neon, argon, etc. With the lithium cation, we start off with a filled 1s shell. Removing another electron, its second ionization energy is pulling that electron from a closed shell. That's a high energy situation. Also, we can see two discontinuities in ionization energy. The first is between group 2A and 3A. That little jump right there. And then the second is between 5A and 6A. That jump there. These occur due to the loss of electron from a single orbital in the first case and the removal of a paired electron in the second case. First ionization energies have a periodic trend as shown. As we go from left to right, the first ionization energy increases, and first ionization energy also increases from bottom to top. Let's apply this trend to a problem. Which atom should have a smaller first ionization energy, oxygen or sulfur? And then which atom should have a higher second ionization energy, lithium or beryllium? In order to answer the question, look at the relative placements of the atoms on the periodic table. For oxygen versus sulfur, both are in the same family, but sulfur is lower on the table. Therefore, it has a lower first ionization energy. For lithium and beryllium, they are in the same period. Therefore, as you go from left to right, ionization energy increases. So we would expect beryllium to have a higher ionization energy. However, when we pull an electron from lithium ion, that is pulling from a core shell. Therefore, the lithium ionization energy would be much larger than the beryllium ionization energy. As a check, are our predictions consistent with the facts shown in data table 8.2? Electron affinity is the amount of energy released when adding an electron to a gaseous atom or ion. In general, nonmetals have more exothermic values for electron affinity than do metals. Now notice that the delta H is negative, but the electron affinity is given as a positive number. Here are electron affinities of some elements. Notice that metals usually have a negative electron affinity. Remember, that is an endothermic process. Many metals, though, have small exothermic or positive electron affinities. Now, in general, as you move from left to right, electron affinity becomes more exothermic, so it increases. And as you move lower on the table, electron affinity becomes less exothermic, or smaller numbers. Here are electron affinities graphed versus atomic number. Notice there are discontinuities between 1A and 2A, and 4A and 5A. These discontinuities exist because we are adding electrons to half-filled shells, which gives electron-electron repulsion, meaning that it is less exothermic adding electrons because of the repulsions.